Hey everybody, welcome back to my channel. In this video we're going to go over linear versus nonlinear ordinary differential equations. This is an important distinction to be able to make because it's going to let us know which methods are available in order for us to find a solution to our ordinary differential equation. But let's go ahead and begin by looking at the definition of a linear ordinary differential equation. Okay, so this looks like a lot, but this is the general form for a linear ordinary differential equation. So a linear ODE is an equation that consists of y, which is our dependent variable, and in this case y is the function that we're actually trying to solve for to get a solution for our ODE. We have derivatives of y, which we can see right here, and in front of the derivatives we have coefficients. Let me change colors for the coefficients. We also have coefficients, the a sub n of x, the a sub n minus 1 of x, and so on. These coefficients are pure functions of x. In this case, x is our independent variable, and the a sub n, that just correlates to the order of the derivative that we have for y. And on the right side of the equation, we also have a pure function of x, which is in this case labeled g of x. This is also sometimes referred to as the forcing function, which will help us determine whether or not our linear ODE is homogeneous or non-homogeneous, which we're not going to get into here, but that's just something to note. Okay, so now let's go ahead and list out these properties. So first off, the coefficients are functions of the independent variable x or constants. A constant is technically a function of an independent variable, but I thought it would be important to note that just so that you can look out for that later, and we will look at a few examples here. Next, our coefficients are not functions of the dependent variable, and in this case, the dependent variable here is y. And our last property is that the dependent variable and its derivatives are only taken to the power of 1. And what I mean by that is we have y, which is our dependent variable, and we have different derivatives of that. But regardless of the order of the derivative, so for example, right here, this is to the nth. This is an nth order derivative of y, but regardless of the order, this is really only just to the first power, because we don't have to annotate this, but this really just says that this is to the power of 1. So we'll see an example of this here in a little bit, but what I wouldn't be allowed to do is take this to the power of 2 or 3 or anything else. Okay, so for our first example, we have sine of t times y prime minus y times cosine t equals tangent of t. And in this case, our dependent variable here is y. That's the function we're trying to solve for. We have a first order derivative, y prime, and then we have our coefficients. So in this case, the coefficient to y prime is sine of t. That is a pure function of t. In my definition, I had the independent variable as x, but that was just for the sake of writing it out. Obviously, you can name your independent variables and dependent variables whatever you'd like, as long as they're consistent. In this case, the independent variable is t, and it is a pure. So sine of t is a pure function of the independent variable. Here we have negative y times cosine t. Since I'm multiplying these, I can really write these in any order. I could just as well write negative cosine of t times y, but this basically says that I have a coefficient, which is cosine of t, in front of my dependent variable y, and that coefficient is a pure function of t. On the right-hand side, I have our forcing function, which is also a pure function of t. It's a pure function of our independent variable, so no issues there. For the next example, we've got 3y double prime plus e to the x y prime plus y equals cosine of x. Here we have our coefficient, which is 3. And one thing that we said is we're allowed to have constants for coefficients. So in this case, 3y double prime, no issue here. We have our coefficient e to the x. Remember, e is an actual number. So e to the x is a pure function of x. In this case, the independent variable is x. So pure function of x for the coefficient, no problem here. We have y, first order derivative of y. And then we have y by itself. And in this case, this implies that we have a coefficient of 1. And then on the right-hand side, we have cosine of x, which is a pure function of x. So no issues here. In this example, we've got x cubed times the second order derivative of y with respect to x minus x times the first order derivative of y with respect to x minus y over x equals the square root of x. And notice we can use different types of notation for our derivatives and the order of those derivatives. So once again, we've got our dependent variable, which is y. We've got various derivatives of it. So we have a first order, second order derivative. Then we have coefficients. X cubed is a pure function of x, our independent variable. Negative x is also a pure function of x. And here we have negative y over x. And this is really just the same as negative 1 over x times y. So in this case, our coefficient is negative 1 over x, which is a pure function of x. No issues. The function on the right-hand side of our equation is square root of x. That is a pure function of x, our independent variable. It's the same thing as just writing x to the 1/2, so no issues here. Okay, next let's look at some examples that actually violate some of the rules, some of the properties we listed out, and these are going to be ODEs that are non-linear. All right, now in this example, we've got y prime minus 2xy equals x cosine y. On the left-hand side of the equation, everything seems to look okay. We have y prime. Here our dependent variable is y. So we have y, we have the first order derivative of it. Here our coefficient is negative 2x, which is a pure function of x. But then on the right-hand side, we have x cosine y. You can think of that as a single function. The problem is we have x, which is our independent variable, but then because it is also a function of x and y being our dependent variable, that means that it is no longer a function, a pure function of our independent variables. Now it is a function of two variables, the dependent and independent variable. So that violates one of the properties of linearity, of being a linear ODE, hence this is non-linear. And in this example, we have the second order derivative of y with respect to x plus the derivative of y with respect to x squared equals 1. And right here, we're violating one of the important properties of our linear ordinary differential equations, meaning that if y is our dependent variable, then for y and any of its derivatives, we can only take those to the power of 1. We can't square those, we can't cube those. And the reason being is in a linear ODE, any operator applied to the dependent variable, in this case it's y, must be a linear operator. So for example, derivatives are linear operators. Let's say I had two solutions, y sub 1 and y sub 2, then the derivative with respect to x of y1 plus y2 is just dy1 dx plus dy2 dx. So derivatives are linear operators. However, when we square something, that is not a linear operator because y1 plus y2 squared is not equal to y1 squared plus y2 squared. So because we're squaring this derivative, this is not a linear ordinary differential equation. Okay, and then for the last example here, I have y double prime plus 3y times y double prime plus y equals e to the x. And the main issue is right here. One of the properties for being a linear ordinary differential equation is our coefficients either have to be pure functions of x or pure functions of our independent variable or coefficients. And in this case, we have a function of our dependent variable, which is why this is a nonlinear ordinary differential equation. So this is just a brief summary of linear versus nonlinear ODEs and some other properties. I hope this helped. If you have any questions, comments, suggestions, ways I could have made this better, I'd love to hear what you have to say in the comment section. But thank you so much for watching, and I hope you have a great day. Take care.